Hi everyone, welcome back to another episode of Once Upon a Lecture. Dorothy and Toto here, directly from Oz, ready to tell you all about measures of dispersion. Let's get started. So here's an overview of the topics we're going to cover today. The first thing we'll do is we'll talk about what measures of dispersion are and how they differ from measures of central tendency. Then we'll talk in depth about each measure of dispersion, which include the range, average deviation, variance, standard variance, and we'll wrap up our discussion by talking about standard scores and z-scores. In our previous discussion we had with Princess Snow White, she taught us about the different measures of central tendency. When we talk about central tendency, we're talking about the mean, the median, and the mode. And those three measurements tend to be clustered towards the center of a normal distribution. If we think about the measures of dispersion, these are in fact quite the opposite of the measures of central tendency. So while knowing the measures of central tendency, like the mean, is helpful, it doesn't actually tell us how dispersed our data distribution really is. So let's imagine if we look at the amount of rainfall that happens in Kansas compared to the amount of rainfall that happens in Oz. We know that the average amount of rain in each city is 12 inches. What we do not know is how this rain is distributed throughout the year. Which months had more rain and which months had less. Therefore, we must look at the measures of dispersion to answer this question. The word dispersion means to be spread apart from. So while measures of central tendency tell us how scores are clustered around the mean or the middle of a distribution, measures of dispersion tell us how far apart the data points are from each other. In other words, how widespread the distribution is. We have four main measures of dispersion: range, average deviation, variance, and standard deviation. Let's take a look at each one of these in more depth. We'll start with the range. The range is the distance between the highest score and the lowest score in a distribution. It is also the quickest measurement of the distribution to identify, and it's also very, very easy to calculate. All you have to do to calculate range is subtract the lowest score from the highest score. So let's imagine I obtained IQ test scores from some people in Oz last month, and these are the scores I found: 13, 23, 33, 43, 53, 63, 73, 83, and 93. So we have a perfect 10-point increment between each data point. If I wanted to calculate the range of these data, I would subtract 93, the highest score, minus 13, the lowest score, and be left with 80. Therefore, 80 would be my range. Now let's imagine that I took another sample of IQ scores a month later, and these are the scores that I get: 13, 85, 86, 87, 87, 88, 88, 89, and 100. If I were to take the range of these data, I would again take the highest score, which is 100, and subtract the lowest score, which is 13, and get a range of 87. So you could see that that first number in my distribution, that number 13, is definitely an outlier from the rest of the data points. If we imagine that the number 13 wasn't there, and our smallest number was 85, in that case, our range would be 15, which would be much more representative of this distribution. However, because that outlier 13 is there, we get a very large range, 87, which is even larger than the range we had in the previous example. So even though the ranges are similar, the scores are very different. The outlier in the second set of IQ scores definitely inflates the range. So let's take a look at the second measure of dispersion, average deviation. Average deviation refers to the distance that each score deviates from the mean. Again, if you remember back to our previous discussion with Princess Snow White when we talked about deviation, if a score deviates, it means that it is different from. And in this case, we are constantly talking about deviation from the mean. So the larger the deviation, the farther it is from the mean, and the greater or wider the distribution. Scores can deviate from the mean by being either higher or lower than the mean. Therefore, if a score is higher than the mean, it typically is a positive difference, and if the score is lower than the mean, the difference results in a negative number. However, average deviation is based on absolute value of these distances and not on the polarity. Absolute value means that even scores that have a negative number are considered to be positive because we are ultimately looking at the distance that score is from zero. The positive or negative signs simply tell us if the deviation is moving above the mean or below the mean. So if we look at the formula for calculating average deviation, it looks something like this. So we can see that average deviation is equal to the sum of every score minus the mean divided by the total number of data points we have. Now, if you're thinking to yourself, this looks familiar, you're absolutely right, because you did learn how to calculate a part of average deviation last week when we talked about central tendency. If we take each data point and subtract the mean, we will be left with some sort of a difference, some sort of a deviation. If we add up all of these differences between the mean and each data point, we are going to be left with the numerator, so the sum of each score minus the mean. We then divide that number by n, the total number of people in our sample, and this is how we calculate average deviation. So if you recall, we also talked about a theory called the mean as the balancing point, in which we learned that the sum of all of the deviations from the mean will always equal zero. Therefore, it doesn't really benefit us to use a measure of dispersion that always results in a value of zero. So that brings us to our third measure of dispersion, variance. Since calculating average deviation always leaves us with zero, we're going to square the deviations before we add them to calculate the variance of the distribution. So when we say squaring a deviation or squaring any number, that means you are going to multiply that number by itself. So first we calculate the difference between each score and the mean to find the deviation. Then we square each deviation so that the positive and negative numbers won't cancel each other out when they are summed together. Essentially, if you have a deviation difference that is -2, and if you add -2 to a positive deviation of +2, you will end up with a 0. However, if you square the deviation of -2, -2 times -2 will give you +4 because a negative times a negative will result in a positive number. So essentially, by squaring the deviations, we're getting rid of the negative numbers. Lastly, once we do that, we're going to divide this sum of squares by n minus 1. So the variance tells us how far a distribution is spread. If the variance is small, it means the data points are close together. And if the variance is large, it means the data points are far apart. And logically, if we think about the word variance, it should remind us of the word to vary, right? To differ. So the more the numbers differ from each other, the farther spread out they will be on the distribution. And conversely, the closer they are to each other on the distribution, the less they will be varying from each other. So let's take a look at the formula for the sample variance. Please do not be alarmed. We will totally dissect this, and I promise by the end of this lecture, you will be a master of the variance formula. S squared is the symbol for variance. S squared is equal to the sum of squares. So that first section, the sum of x squared, means that we're going to square each score and then add up the total of every score once it is squared. Then we are going to subtract the sum of x and then square it. So if we talk about the sum of x, that means we're going to add up each score only once without squaring it. We're going to add up each score and then square that total. So this is different than the sum of x squared that we saw in the beginning of the formula, because the first one refers to squaring all the numbers and then adding up the total of the squared numbers. The second part says we're going to add up the total of the x column of the scores and then square it. And also, we're not quite finished with that section. Once we square it, we have to divide it by n, the total number of data points in our sample. So you kind of have a tricky numerator that also has a denominator in it. So you kind of have these two denominators. And so order of operations is extremely important here. The parentheses indicate the parts that you should solve for first. So once you calculate the sum of x squared, you're then going to subtract the entire entity of the sum of x then squared divided by n. So then you should have only two numbers in the numerator and not have an extra fraction. Once you calculate that difference, then you can go ahead and divide by the denominator, which is going to be n minus 1. So the number of data points in the sample minus 1. If you have scores that occur more than once in a distribution, then we have to take that into account. We have to make sure that we take frequency into account when calculating variance. So if we do have a frequency distribution, the formula slightly changes, but again, nothing that you haven't seen before. We simply have to add the frequency into the formula, symbolized by a lowercase f. So in this case, we have the sum of f of x squared minus the sum of f of x then squared divided by n, all over n minus 1. So you may recall from our previous discussion on measures of central tendency, when we learned how to calculate the average if we have a frequency distribution, you will remember that that f of x column, meaning we have to multiply each frequency by the score, is the same step we're going to have to take in order to calculate variance. The last measure of dispersion we're going to talk about is standard deviation. So while variance tells us the average of the squared deviations, the standard deviation tells us how much variation from the average there actually is. So the good news is that mathematically, standard deviation is also the square root of variance. A small standard deviation suggests that data points are close together, just like with variance. And a large standard deviation indicates that the data points are far apart, just like with variance. So if we look at the formula for standard deviation, it looks identical to the variance formula, but instead of having s squared, we now have s, because the square root of s squared will leave us with s. So essentially it's the same exact formula, but the square root of it. So typically it's often easier to calculate the variance and then take the square root of the variance to find the standard deviation. So if we take a look at how standard deviation relates to the normal curve and the normal distribution, let's take a look at the x-axis on this graph here. In the center, we have mu. Mu represents our mean. In this case, it's our population mean. If you notice, the distribution goes from -3 to +3. So the graph is split almost into 6 equal parts. Each of these parts refers to a standard deviation. So in a normal curve, each standard deviation is equal to 1, and the average is equal to 0. So once we calculate a standard deviation, we can then plot it somewhere on the normal curve to see where it falls. So as a reminder, we know that majority of scores on a normal distribution fall somewhere between -1 and +1 standard deviations, which means about 68% of the entire 100% of the distribution will fall somewhere between 1 deviation below and 1 deviation above the mean. Again, this is a great illustration of the idea of central tendency. We can see how majority of the scores tend to be clustered around the mean. As you go out farther to each end of the standard deviations, -2 and +2 houses only about 14% of the distribution, so much less than the 34 within the positive or -1 distribution. And as you go farther out towards the edges of the normal distribution, you see that smaller and smaller percentage of the population falls within that area. Once we understand how standard deviation can be calculated, we can then apply it to standard scores, also known as z-scores. Standard deviation tells us how far a score deviates from the mean in standard units, called z-scores. So z-scores, in other words, are a deviation of the raw score from the mean in standard deviation units. The sign or the polarity of the z-score tells us which direction the score is relative to the mean. Once again, a positive z-score would indicate that the raw score from which we've converted is above the mean, and a negative z-score suggests that the raw score is below the mean. The formula for converting a raw score into the z-score looks like this, where z is equal to the z-score that we are solving for. X represents the raw score in your data set. X bar represents the average or the mean, and we divide all of that by S, the standard deviation. So essentially, you can only calculate a z-score, you can only convert a raw score into a z-score if you have already calculated or you already know the standard deviation. So the three elements that you need are the data point, the average, and the standard deviation of your data set in order to calculate your z-score. However, we can also calculate the reverse. If we know the z-score, we can then calculate the raw score. Basic algebra. So if we take a look at this formula, we can see that x, or the raw score, is equal to the z-score multiplied by the standard deviation plus the mean. Again, order of operations, really important here. It's really easy to make a mistake if you add or multiply in the wrong order. So remember, multiplication supersedes addition. So the first thing you want to do is multiply the z-score times the standard deviation, and then that whole unit, add it to the average. So we've talked about a lot of different calculations. I think it's time that we try it together. Let's consider this example. When I first landed in Oz, the Munchkins told me about their encounters with a wicked witch. Here are the number of times each Munchkin reported having an encounter with her. So taking a look at this data set, we can see scores 27, 36, 42, 12, 18, 15, so on and so forth. So let's try to find all of the measures of dispersion for these data. The first thing we need to do is organize the data. By looking at the numbers, do we see any that occur more than once? If you're thinking to yourself, yes, then you're absolutely right. So we know if a score occurs more than once, it means we have frequency. Because we have frequency, we need to put them into a frequency distribution. If we remember, the frequency distribution is typically created in descending order. So we'll start with the largest number at the top and we'll work our way down to the smallest number. By looking at this distribution, we can see that 42 is the largest number in our data set and the smallest number we have is 2. So our frequency distribution will go from 42 all the way down to 2. All right, now that I have my data in a frequency distribution, I can start calculating my measures of dispersion. Let's start with the range, since that seems to be the easiest one. Remember, the range is equal to the highest score minus the lowest score. In this case, 42 is our highest score and 2 is our lowest score. So 42 minus 2 gives us 40. Therefore, the range is 40. Nice job. Next, let's calculate variance. Remember, the standard deviation is the square root of the variance. So if we find the variance, we can just take the square root of that value and then find the standard deviation. Let's take a look at that variance formula one more time. Because we have an F column and we have frequency, we're going to have to use the formula that takes the frequency into account. So again, we have the variance is equal to the sum of f of x squared minus the sum of f of x then squared divided by n all over n minus 1. So because we have all of these sums of f of x, it looks like that's the first column we should try to calculate. So let's go ahead and set up our f of x column. Remember, if you see two symbols side by side each other, that means that the two numbers need to be multiplied. If I see f and x side by side, that means I'm going to multiply the number in the x column by the number in the f column. So the first thing we need to do is multiply each score by the frequency to complete this f of x column. Once we do that, we're going to add up this column to get the sum of all of the scores times their frequency, which is going to be the value that goes into the second part of our formula, the sum of f of x. Once you calculate your f of x formula, you should get something that looks like this. If my score is 42 and my frequency is 1, 42 times 1 will give me 42. 36 occurred with a frequency of 1 time. 36 times 1 gives me 36. So if we go down to a score of 21, we can see that 21 occurred twice. Therefore, I have to multiply 21 times 2, and I'm left with 42. Once you do this for all of the scores from 2 all the way to 42, we are then going to get the sum of this column. And as we can see here, the sum of this column is 378. This number, 378, is going to take this part in the formula. It is the sum of f of x. Remember, we haven't squared anything yet, so it can't be the first one, the sum of f of x squared. This has to go in the second section, the sum of f of x. Next, we have to square each score, each x value by itself, and multiply that by the frequency. So go ahead and set up an f times x squared column. If I look at my first value of x, I see 42. If I multiply 42 times 42, that is my x squared value, then I need to look at how many times that number 42 occurred. If I see that the frequency is 1, then all I do is multiply 1 times 42 squared. Then I look at the next value I have, which is 36. 36 occurred 1 time, so I'm going to do 1 times 36 squared. You're going to continue doing this for all of the ones that have a frequency of 1. And then, for example, let's look at a score of 21. The score of 21 occurs 2 times. So what I'm going to do is I'm going to square 21 by itself, and then I'm going to multiply it by 2 because this time my frequency is 2. So taking a look at this column, f times x squared, this is a breakdown of what that column should look like. Again, all you're doing is multiplying frequency, the number of times a data point occurred, times each score squared. The next thing we have to do is add up this column to calculate the sum of the squares times the frequency. This is going to give us the sum of the f of x squared column. We see that that total is 8,686. This number is the sum of f of x squared, and this is the number that's going to go in the very first part of our formula. So far we've calculated the sum of f of x squared and the sum of f of x. The next thing we need to do is calculate n. Remember, n represents the total number of data points you have in your sample. If we add up the frequency, the f column, we can find how many data points actually are in our sample. If you notice, the sum of the numbers in that f column add up to 20. So 20 is going to be our n, and 20 minus 1 would be 19. Now that we have all of the values we've calculated, we can plug them into the formula. So the first number, the sum of f of x squared, is 8,686. We are then going to subtract the sum of f of x, which is 378, then square it and divide by n, which is 20. All of that in the numerator is going to be divided by 19. So if we simplify this a bit further, if you take 378 squared divided by 20, you're going to be left with 7,144.2. So essentially the second part of the formula here is the simplified version of 378 squared divided by 20. Now we have no fractions left in the numerator, and all we have to do is subtract 8,686 minus 7,144.2, and that difference is going to be divided by 19. So once we do that, we are left with the variance of 81.15. So our variance is equal to 81.15. That sounds like a pretty large variance, so this suggests that our data points are pretty spread out. If standard deviation is the square root of variance, all we need to do is take the square root of 81.15 to calculate it. So the square root of 81.15 is going to be 9.01. Therefore, our standard deviation is equal to 9.01. So if we go back to our original question, when I first landed in Oz, the Munchkins told me about their encounters with the Wicked Witch. These were the data that we came up with, and our goal was to find the measures of dispersion for these data. We found that the range is equal to 40, variance is equal to 81.15, and standard deviation is equal to 9.01. You may be thinking to yourself, well, gee, what happened to average deviation? Well, that's true. We didn't calculate average deviation because we already know that we would put all this effort into creating more tables and more calculations to ultimately end up with a total of 0, because remember, the numbers on the positive end cancel out the numbers on the negative end, and we're always left with 0. That's why even though it is a measure of dispersion, it is not one that is of any use to us. So now I'd like us to practice calculating some z-scores, aka standard scores. Remember, the purpose of calculating z-scores is to understand where these raw scores can fall on a normal distribution. Let me remind you about the formula for the z-score. The formula says that z is equal to the score, represented by x, minus the mean, divided by standard deviation. So let's imagine that the average number of witch encounters per month in Oz for 33 munchkins is 21.65, with a standard deviation of 2.83. Let's try to convert the raw score of 19 and the raw score of 25 into a z-score. So again, the formula says that we have to subtract the score from the mean and divide by standard deviation. So in this case, my raw score is 19, my mean is 21.65, and my standard deviation is 2.83. So let's plug those numbers in. 19 minus 21.65 divided by 2.83 gives me a z-score of negative 0.94. The fact that it's negative suggests that the raw score is below the average. If we look back up to the top of the problem, we are told that the average is 21.65. This is the raw score average. We are asked to convert a raw score of 19 into a z-score. So you ask yourself, is 19 greater than or less than our average of 21.65? Clearly, 19 is a smaller number, therefore it's going to be smaller than the average. So the fact that the z-score is negative shouldn't surprise you. It makes perfect sense because 19 is smaller than our average. Now let's take a look at the score of 25. Even here, you can think to yourself, is 25 greater than or smaller than the average of 21.65? 25 is in fact larger than 21.65, so we can assume that this z-score will be positive. So once we plug this in to our formula, we place 25 in place of x, subtract 21.65 and divide by 2.83, and we are left with a positive z-score of 1.18. So because we can see that the first z-score is negative, it tells us that this value is below the mean. We can also say that a score of 19, a raw score of 19, is almost one entire standard deviation lower than the mean. Remember, z-score is another word for standard score, or a way for us to locate where on a normal distribution a standard score can fall. And because we know that standard scores are relative to standard deviations, we can say that the raw score of 19 falls almost one standard deviation below the mean. Similarly, we can see that a z-score that's positive is going to be above the mean. So a raw score of 25 is more than one standard deviation, but to the other side, above the mean, because it's going to be higher. We can also calculate a raw score if we know the mean and the standard deviation of a given z-score. So if you think back to the raw score formula, where x represents the raw score that we're trying to calculate, is equal to the z-score multiplied by standard deviation plus the mean. Again, order of operations, make sure you multiply z by s before adding the average. So if we have a mean of 21.65 and a standard deviation of 2.83, what score is 1.5 standard units below the mean? The word below is a good indication that the z-score has to be negative. So using our formula, x equals zs plus x bar, all we have to do is plug in the values. X is equal to negative 1.5. Negative 1.5 represents the z-score that was given to us in the question. So the words, what score is 1.5 standard deviation units below the mean is another way of saying z-score of negative 1.5. So we put negative 1.5 into the place of z. We multiply it by 2.83, which is our standard deviation, and lastly we add the mean. So ultimately we are left with a raw score of 17.41. So to answer the question, what score is 1.5 standard deviation units below the mean? The answer is 17.41. Remember, our mean was 21.65. 17.41 is certainly lower than 21.65, so it looks like we're on the right track. So let's take a look at how that data point would fall on a normal curve. On a normal curve, in a normal distribution, 0 represents our average in standard deviation units. And we have 50% of our data points that fall within positive 3 standard deviations above the mean, and the other 50% that falls up to 3 standard deviations below the mean. If we plot a standard deviation unit of negative 1.5, that's going to be to the left-hand side of the mean, somewhere between negative 1 and negative 2 standard deviations below the mean. So while the mean is 0, we can see that negative 1.5 will fall somewhere to the left of the mean. Let's try another example. If we have a mean of 21.65 and a standard deviation of 2.83, what score is 2 standard units above the mean? Now here the key phrase above the mean is a good indication to us that the z-score is going to be positive. In our previous example, the deviations were below the mean, so we had to make it negative. If the question asks you about deviation units above the mean, then you know the z-score will be positive. So once again, using the same formula, we're going to plug in those values. This time, the number 2 is going to take the place of z because 2 represents 2 standard deviation units. In other words, a z-score of 2. And we're going to multiply that by the standard deviation of 2.83 that was given to us and add it to the mean of 21.65, which was also given to us in our question above. Once we calculate that, we are left with 27.31. A raw score of 27.31 corresponds to a z-score of positive 2, or 2 standard deviation units above the mean. Here's how that data would look on a normal curve. Once again, 0 represents our average in standard deviation units. Because we know z-score of positive 2, in other words, 2 standard deviation units above the mean, we're going to go to the number 2 to the right-hand side of the mean and draw a line there. So that represents the amount of the population who would have scored 2 standard deviations above the mean. So I know that was a mouthful of information. Just as a quick recap, in this lecture, we talked about measures of dispersion, including range, average deviation, variance, and standard deviation. We learned that standard deviation is the square root of variance, so they are very, very much related. If standard deviation or variance are large, it suggests that our data points are dispersed a lot and our distribution is wide. If variance and standard deviation are small, it suggests that there is not a big difference between data points on a whole and that distribution will be more narrow. And lastly, we talked about the fourth measure of dispersion, average deviation, which is kind of useless since it always results in the value of 0. So hopefully you found this lecture helpful, and Toto and I will see you next time on Once Upon a Lecture. Bye!